basically that A3 by A0, you call it W. That is a coefficient of lambda. So the W divide it. So divide it and take it to the left-hand side, this operator here. Whatever is here, take it this side. 1 by Wx ddx of Px dy by dx plus Qxy equal to lambda. This looks like your operator L acting on Y equal to lambda. This is your eigenvalue problem where the operator is this one. Okay. Can you see this one? In this, the W has to be non-zero. That is the case. Okay. So you can't put any other thing. So except that A3 should be always be positive and should not be non-zero. And you normally assume that it is greater than 0. Okay. That's a weight function. So now once you see this one, I'm going to, based on this operator, I'm going to define the dot product there. So it's like, now you're studying, so that inner product, dot product or inner product, all are same. Okay. So dot product in your finite dimensions is simple usual dot product. In your infinite dimensional spaces, for example, L2 space, you have this dot product. There is also norm, it becomes. So you see the all are connected. This is a distance, right? So that is fx gx bar dx. You have a weight function now because of the W, that W you're going to put. This is the definition. So with respect to this dot product, your operator L is basically the symmetric or self-adjoint. We call this Hermitian. Okay, Hermitian, self-adjoint, all these are same words. So what is the meaning? LFG equal to, so L acting on F and G, you take the dot product, you bring this L onto G, that is both are same, and it is both are same for every F and G. Okay, then you say that this is L is basically self-adjoint operator. So you start with, how do you see this? How do you see that both are same? You start with LHS. So if you start with LHS, so what you are seeing is LFG, that is basically this one, and this is equal to this one. So now you write it. What is your LF? LF is basically your operator acting on F. Wx is already there in your definition of dot product. This W gets cancelled, and you finally get like this. Now you operate this ddx, you take it onto the, do the integration by parts basically. You're doing the integration by parts, Px df by dx, G bar, this is the G bar other function. So first term I'm doing integration by parts. This one plus derivative of G dash. So that's what is this one, this integration by parts. The second term as it is, I kept it. Okay, that's what it is. You stop me if you don't understand. Okay, so now what I do is, again I try to do one more integration by parts for this one. So how I'm going to do this is this ddx. Okay, this as it is there first term and the second term, and you see this here only df by dx is your one function, and px into dg bar by dx is another function. So this antiderivative of df by dx, that is your fx, remaining as it is you write, and you have a to b, that is our boundary term, minus that now in the integration part, this is the second term, this is what you have, and this as it is. Now you see the boundary terms, you put them together, it will be like this one, and you now combine this one, these two terms, whatever this term integration, where the derivative is taken here and on the G bar, and here this part, if you put them together, you see that is actually FLG, both are same. Okay, F into 1W and W, you just multiply and divide, so you will get your this one. Okay, acting on LG of L is actually without any conjugacy. Okay, so you have a ddx, those are all real. So you put L bar of LG is nothing but LG bar. Okay, so this is this together. Once you write it, this is nothing but F dot product with LG. So you have LF dot product with LG same as F into LG, provided this boundary terms equal to 0. Now that's what you will do with your Sturm Liouville problems. Now, what is the Sturm Liouville problem? Regular Sturm Liouville problem is Ly equal to lambda y, where L is this operator. You can always, any second order differential equation, you can always put it like this. When I look it as a eigenvalue problem, you write like this. And when P, this P corresponding to some P is 0 at both the ends. You have a derivative, you have the domain, no? Domain is basically x belongs to AB. Okay, x belongs to AB is your domain. So at A and B, this P function is non-zero, which is the case now. If you actually see here, what is your definition of P? E power integral this thing, no? Generally A1 by A0. So exponential function is always greater than 0. So that's how it is. Okay. So this is how you are seeing. So this is always greater than 0, Px. P of A can be 0, okay? But P of 0, P of A, P of B. Because you see, whatever you are doing is only in the open interval, right? P of X. But at the end points, it can be 0 also, certain equations. But in this case, whatever you started with, if it is not equal to 0 at P and A equal to B and X equal to A and X equal to B, then you say that is a regular sturm Liouville system. Okay, regular sturm Liouville differential equation, and then Q can be positive or negative, and W is always positive, you assume, and you give a boundary conditions. Boundary conditions, this is the second order equation. You give the boundary conditions of y and y its derivative at A, and y derivative at B with some coefficients. How we take this coefficient is like not both of alpha 1, alpha 2 are 0, or not both beta I, beta 2 are 0. Okay, that is same as saying alpha 1 square plus alpha 2 square not equal to 0. That means not both of them are 0. Okay, that way also you can put it. So this together, that is called sturm Liouville problem. So whatever we wrote here, so this is your sturm Liouville problem. So this is like your eigenvalue problem. Eigenvalue problem functions and it will have, because it is self-adjoint operator, it is looking like your symmetric matrices. Symmetric matrices will have only positive real eigenvalues, and it has same number of, it will have all the eigenfunctions. Eigenfunctions here, eigenvectors for your matrix. Okay, so those are eigenvectors. They form complete orthogonal. They are actually orthogonal and they are complete. Complete means any vector I can write in terms of these eigenvectors. That is the meaning. They form a basis. That's what it means. Okay, so in the infinite dimensions also, you can calculate. You need to find all your eigenvalues, and eigenvalues are always real. Okay, so you have always real eigenvalues, and then it will have eigen functions here. You don't call them eigenvector. Here you call them eigenfunctions. Eigenfunctions will be forming complete orthogonal eigenfunctions. Okay, so we'll see how it is why in the regular sturm Liouville system. So this all you do joint. So for that, with this regular sturm Liouville system, you easily see that this quantity will be 0. The boundary term quantity that you are seeing now, then only it is self-adjoint, right? So whatever, if you define as your, this is for your regular sturm Liouville system, LFG is same as FLG, provided these boundary terms are 0. Those boundary terms, because of these boundary conditions that you give, provide for your regular sturm Liouville system, these boundary terms now in your that is actually 0. So that's what we are showing here. So Ly equal to 0. Okay, y is a problem, right? So y1 and y2 be two solutions you take, for example. Okay, so then it satisfies the boundary conditions. I am writing y1, these two and these two, and you consider first one and this one and this one, this one and this one. If you consider at A, this is what you have. So if you write it as a system of equations, as a matrix form, you have, this is our matrix into alpha 1, alpha 2 equal to 0, 0. So alpha 1, alpha 2, we know that not both of them are. So that means you have a non-zero solution for this Ax equal to 0 system. So that means the determinant has to be non-zero, right? Otherwise, if it is non-zero, then what will happen? If the determinant is actually non-zero, implies alpha 1, alpha 2, both of them have to be 0. But that is not what you started now. Your boundary conditions, both alpha 1, alpha 2 cannot be 0. So that implies that this determinant is 0. So that is exactly what you have here. One term, PA into, so this is equal to 0 implies what? PA is also non-zero, no? So non-zero quantity into this 0 quantity equal to 0. So that is what exactly what you have, one of the terms when you put x equal to A. Okay, so that is how you are getting your this term is 0. Y1, y2, no? So here F and G are solutions finally. Okay, F and G are when you consider, those are actually your solutions. Okay, so that is a similar way you can also do at B. If you look at other two equations, if you consider at B, then it becomes same way for the same argument. At B also it is 0. That implies both of them are 0. This quantity in that LF equal to G, this dot product, so that you see that this is actually self-adjoint. So self-adjoint, Hermitian or skew symmetric is actually symmetric. Okay, Skew symmetric, you don't say. Okay, generally skew symmetric means what? With what is a skew symmetric matrix? A bar transpose is same as A, right? A bar, right?
Yes, sir.
A bar or A? That is your A star equal to A, no? So this is what is the meaning of skew symmetric. Okay, it is actually symmetric. Skew symmetric means you consider this complex quantity also, okay, entries. But all our entries are real because you're dealing with differential equation solutions. Those are all always real. So one of those properties that I'm not going to go for the proof. Once you see that these are Hermitian, self-adjoint, or skew symmetric, whatever, L is self-adjoint, you see it as only self-adjoint. Okay, self-adjoint operator. Eigenvalues are always real, and eigenvalues, eigenfunctions you calculate, they are always real, and eigenfunctions are orthogonal. Okay, if they are not orthogonal, you can make them. When is this possible that they are not orthogonal? They are independent. They are always independent. Something like, if you have same eigenvalue you may have, you will have corresponding eigenvectors you will form v1, v2. They are actually independent, but they are not orthogonal. You can make them orthogonal by Gram-Schmidt process that you already know. Do you know that Gram-Schmidt process?
Yes,
Yes,
sir.
sir.
Yeah, through that process you can always make them, even if they are not. But you know that the distinct eigenvalues will always have orthogonal, always orthogonal. That result you know from linear algebra. Only repeated eigenvalues, it is possible that the eigenfunctions or eigenvectors, they need not be orthogonal, but they are independent. So it's like in your plane, two vectors are like this. You can make them orthogonal by Gram-Schmidt process. One you keep it as it is, other one you try to convert like this. Okay, just with by using this first one. Okay, that is what is the orthogonal or the Gram-Schmidt orthonormal process. So you can make them orthogonal. Okay, like that you form a complete orthogonal set of eigenfunctions. So what is the meaning of complete? Complete means any function I can represent it as a in terms of these eigenfunctions. That is exactly your Fourier series. Okay, so it's your Fourier series. Now you use the dot product to this with these Vn's because they are orthogonal. Vn's are orthogonal functions, right? So using that, I can calculate these constants, Cn's. Those are your Fourier coefficients or Fourier transforms. Okay, these are Fourier transform. This is actually Fourier series. Fourier coefficients, Fourier series. Are saying if you say this is your Fourier transform, this is your inverse transform. Getting back your function in terms of those Vnx. So this is how you get your naturally some Fourier series. All Fourier series are simply putting as one sturm Liouville problem. Okay, so just to give you one example, is here is this one. So find the eigenvalue and eigenfunction of this regular sturm Liouville. Simple one that I consider. Simple boundary conditions you have. So domain is 0 to 1. You calculate. So it is a self-adjoint form always. What is P you identify? P you identify, Q identify, W is 1. So your dot product is this. Self is, you know that it is self-adjoint because it is satisfying your regular sturm. Just now we proved. Now you calculate. So you know that always lambda is always real because it is self-adjoint. So you look at the three cases: positive, equal, less than. So in all the three cases, you try to solve the equation, differential equation. So if lambda equal to mu square, positive case, you differential equation is this, and you calculate. You look for how do you find the solutions of this second order equation? E power kx. You look for complementary function k square plus mu square. So you'll have solution will be cos mu x plus sin mu x with coefficient c1, c2 arbitrary constants. Now you apply your boundary condition. Y0 equal to 0 will give me c1 equal to 0. Okay, so then your solution will become this one, C2 sin mu x. Now you apply the other boundary condition, then you should get this one. So I'm just looking for certain lambda values, right? Those lambda values for which you are looking for non-zero solutions. So for example, C2 is also 0. Suppose C2 is 0. Sin mu can be 0 no, for certain mu values. That means for those mu values, C2 need not be 0. That means I'm having non-zero solution for those values. So I'm looking for such a thing. So sin mu equal to 0 will give me mu equal to n pi. So that means minus mu square, that is your lambda, right? Lambda equal to, lambda is actually equal to, here I put it in this form, no? So in this form is lambda equal to minus mu square, right? So if you put it like Ly equal to lambda, lambda is actually minus mu square. I'm actually looking at the third one. So third case, I'm looking at it. Okay. So this is the case I'm actually looking at it. If you If you see, okay, lambda is less than 0 case only is this one, the one that we are considering. Okay, so sin mu equal to 0 will give mu is n square pi square. So finally lambda equal to minus mu square, that is minus n square pi square. Those are your eigenvalues. Corresponding eigenfunctions are simply non-zero solutions. For example, what is a non-zero solution? C2 can be non-zero when psi mu equal to n pi. So those values, for those values, you have a C2 is non-zero, you take it as 1. So sin mu x. What is sin mu x? Mu is n pi. So sin n pi x are eigenfunctions corresponding to lambda equal to minus mu square, which is minus n square pi square. Have you understood? Now you look at the other cases, lambda equal to 0, for example. Lambda equal to 0, you look at this one. Lambda equal to 0 means this is the equation. This is your solution, general solution. Apply those boundary conditions, both I will C1, C2 are forced to be 0. So that means identically I get a solution as 0. That means it is not an eigenvector. Okay. Similarly, lambda less than 0 will give me this equation. This looks like mu, right? Lambda is always positive. Okay, that type. Ly equal to lambda y, if you write it, Ly equal to lambda y, if you write it, you are seeing that it is actually lambda is actually here, it's positive. So in this case, you see that exponential function as a solution. Apply the boundary conditions. Y0 0, y1 0 will give me. Finally, both C1, C2 are 0. So that means this is also not an eigenvalue. So the only eigenvalues that you found are minus n square pi square, and eigenfunctions are they are simply equal. Okay, sin n pi x are eigenfunctions, and these eigenfunctions, because they are corresponds to all different, n is from 1 to 3 onwards, right? So those are all eigenfunctions. These functions are orthogonal. This is known. Okay, we're not showing it, but that's how it is. Okay, they are always orthogonal. So the theorem that tells you that once you have a self-adjoint operator, eigenvalues are real, corresponding eigenfunctions form complete orthogonal set. Okay, that's what we mean. So they are orthogonal. So with respect to what? With respect to that dot product that we define based on the whatever is your Sturm Liouville system. Okay, so then what is the meaning of that completeness? Any function, any square integrable, for example, if you take, and that any function I can represent like this, that is your Fourier series. Now, what is my Cn? Cn's I can get it by multiplying both sides with your eigenfunctions. Make a dot product. You make a dot product, everything else will go on the right side, only Cm, whatever you multiplied, sin m pi x you multiplied both sides, that is what that particular term only will be there, right? Because of orthogonal functions, right? Because sin m, n pi x are all orthogonal. So that makes it this will contribute here, Cm is equal to this one. This sin m pi x by sin m pi x dot product may be 1 over 1 by 2. Okay, so that's what becomes 2 times of this one. This is actually your Fourier transform. This is actually your inverse Fourier transform, fx equal to this. That is called Fourier series. Okay, because your Fourier series on a finite time signal, you always get Fourier coefficients. Those are your Fourier transforms, and your Fourier series is actually Fourier inverse transform. Okay, that's what is this. This is how you get your Fourier series in general. Now we'll try to look at what usual Fourier series that you see. Those are usual Fourier series. What happens is that you get usual Fourier series. You will get basically your system is not no more regular periodic, regular Sturm Liouville system. This is called periodic Sturm Liouville system. So you have Ly equal to lambda y, same equation. Only thing is at a, b, it is like a periodic. P of a, P of b non-zero. And your boundary conditions, if you change, for example, if you are changing, these boundary conditions are basically here, y at a equal to y at b, and y dash at a equal to y dash b. It's like your periodic boundary conditions. Periodic boundary conditions are simply period. Okay, at a and b, both ends, both values are same. So these are called periodic boundary conditions. If you, for these boundary conditions, if you put it, then you can show P of B into this minus that whatever terms. Now you have to first show that L is self-adjoint. You can easily see P of A equal to is not equal to 0. No, P of A is not equal to 0. But if you look at this part will be, because using these conditions, y at A, y at B, no, f at A, g at A, right? F at A, g at, okay, this term alone won't be there, but together it is 0, because FA and FB both are same, no? Isn't it? Hello? How do you see this one? For example, if P of A, P of B is not equal to 0, Y at A, Y at B. So yeah, B terms I can put it like, again, put it like F at B is actually here. So I wrote it as F at A because Y at A equal to Y at B. So F at A equal to F at B. So F at B, wherever B is there, I can replace with A. So then this minus this is both are same, that is 0. So that means L is self-adjoint. Okay. Similarly, there is another Sturm Liouville system that you might have seen that is called singular Sturm Liouville system. For example, your Legendre equation, Bessel equation, these are all there. You can put it. That is also second order equation, no? So those are all your singular Sturm Liouville system because your equations are where in the equation P of A, either P of A equal to 0, P of B equal to 0, or both of them are 0. In that case, you say that it is singular Sturm Liouville system. So wherever it is 0, 0, case 1, for example, 0, only at A, you have to put your boundary condition like this. B at B, you have to put some other boundary condition. Okay. So these are, this actually case means this is a corresponds to both are 0. With this both, this is your case 1. Case 1 is P of B both are 0. That's why I put boundary conditions like Y at A, Y dash at A, both are finite. This is the boundary condition you have to put it. Okay. So with this boundary condition, you say this is a Sturm Liouville system, singular Sturm Liouville system. Case 2, for example, either one of them. So in this case, at A, for example, P of A equal to 0, then you give this one. And at B, you give usual boundary condition like earlier, regular Sturm Liouville system, whatever boundary conditions you give, no, that is here. Similarly, at B, if you want either this way or whatever, okay, so you can give the second only like that because P of A equal to only 0, but P of B is not equal to 0. That's why we give usual regular Sturm Liouville boundary. In that case also, it is Hermitian. So how do we see that is Hermitian? You can easily see again. How do we see this one? P of B, suppose P of A equal to 0. This is anyway 0. P of B is also 0, right? So these are all you need, whatever these quantities are needs to be bounded. So F and its derivatives are bounded. So this whole quantity is like finite quantity. Finite quantity into 0 is 0. Like that, it will be 0. But this quantity is always 0, right? If for other boundary condition, if you are using, for example, at B, Y at B equal to 0 is anyway 0. Okay. So that way, this quantity we have already, like in the regular Sturm Liouville system, is always 0. If both are 0, then is already P of A, P of B equal to 0. And this quantity is finite. So 0 into finite is 0 minus 0 into finite. So that's how it is self-adjoint. So that boundary terms are 0. So that means L is self-adjoint. So in all the three systems, like singular periodic system, singular system, these are all, these equations are basically self-adjoint. So now we take the periodic system, let us say. Periodic system, simple periodic system in the domain A to B, if you consider Y double dash plus lambda Y equals. I'm taking only one example, okay? Such a periodicity is like Y at A equal to Y at B, Y dash at A equal to Y dash at B. So this is identify what is your P. P is non-zero, P of A, P of B1. And the dot product I identify, Q is 0 here, W equal to 1. So you have this one. And you have this L is self-adjoint. So all eigenvalues are real. And these are the three possibilities. Okay. So each possibility, you try to solve the equation. So let's look at lambda positive case. Lambda positive case means, actually, what is that lambda positive case? So lambda positive. So that means it becomes, I'm actually lambda negative here. So, okay. You have to understand lambda equal to minus mu square I'm putting. Then only you can put it here minus mu square. So that is equation becomes plus mu square. Okay. So this needs to be lambda as actually less than 0 case. Okay. That's a small thing that you need to see. Correct yourself. Okay. So what is the solution? General solution is this one. C1 cos mu x sin mu x. Now you apply this one. If you apply this boundary condition, periodic boundary condition, you get one equation 1. Apply the other boundary condition, you have another equation. Okay. So other equation, both are in C1, C2. You put it like this as a system of equation, these two. C1, C2, you need to identify. So you want C1, C2 to be a non-zero solution. So if you want non-zero solution, the determinant has to be, A determinant has to be 0. Otherwise, if determinant is non-zero, then C1, C2 obviously will be 0, but you're looking for non-zero solution. Your eigenfunction, bro, always non-zero. So that's why this determinant has to be 0. This determinant is 0 will give me actually cos mu A. See, you try to see this one. This square minus plus This is what you will get. So this cos square plus sin square mu at mu a, that is one. So similarly, cos square mu b plus sin square mu b, that is another one. So that makes it 2 minus those 2ab terms will be like this. So finally, what you are seeing is 1 minus cos mu into b minus a equal to 0. Determinant equal to 0. Right? That gives me exactly what is my mu into b minus a is 2n pi. At 2n pi, cos value is 1. So that then is from 1, 2, 3 onwards. Because mu square, lambda is negative, no? Minus mu square. Mu is always positive. So that's why n is from 1, 2, 3 onwards. This is your mu. Okay. So at this mu values, you will have a non-zero solution. We still don't know what is that non-zero solution. So cos mu a minus cos mu b is not equal to 0, or sin mu a minus sin mu b is not equal to 0 if a is not equal to b. Okay. So anyway, a is actually not equal to b, right? So a and b are separate in the periodic case. So for example, 0 to 2 pi, a is 0, b is 2 pi. So in that case, usual your Fourier series you get back. So that's what we are seeing here. So eigenvalues are these. Okay. These are your eigenvalues because lambda equal to mu square, right? That is what you have. Actually, lambda equal to minus mu square. So that's what the minus I have to put it. Okay, so those are your eigenvalues. Eigenvalues doesn't matter. So you have these eigenvalues, but eigenfunctions, those are the functions we need exactly. So to find these eigenfunctions, you take the equation 2. So you solve the basically how do I solve the? I'm looking for, you know, that C1, C2. I have to solve this 1 and 2 and look for some solutions. I need to find some C1, C2. Go back and substitute here C1, C2. Then you will get your solution, non-zero solution. So from equation 1, 2, I think. Okay. So from equation 2, look at this equation 2. You have C2 given in terms of C1, or C1 is given in terms of C2. So whichever way you write. Okay. So put this one into the equation 1. Basically, you are solving both the equation 1 and 2. From equation 2, you get C2 in terms of C1 or C1 in terms of C2. Whichever calculation you do. From this, you put this into equation 1. Equation 1, if you put it, what you are getting is you substitute this one. 1 minute. Hello. Hello, who is this? Hey, class ra. Okay, see, you substitute this C2. You substitute this C2 in here. So you see there, substitute that C2. I'm putting a C1 into this part, into the second equation. Okay. Similarly, here C1 in terms of C2, if you want, you can put it here in the first equation. Okay, either this or this you will get. So you see here, C1 is common. I take it out. The denominator is also common. Take a LCM. So you will see what you get here. This implies, what is this? This gives you implies 2, either this or this will give me. This also will give me the similar thing. C2 is common here. Either this you will get, or so either this you will get, or you get this one. Okay. This or this, because we're looking at two ways. So you will see that 2 into this also becomes 2C1. This is non-zero. This is non-zero. Denominator is non-zero because A and B are not equal to 0. So you can easily see that one. Okay. So that means this has to be 0. So this anyway, we know that this is for those mu values only we are calculating, right? This is equal to 0 because those mu values is equal to 0. That means C1 I can take it as arbitrary. I can take C1 to be non-zero quantity. Similarly, for the same reason, either this case also, C2 also can be arbitrary. So what is that you found actually? C1, C2 are arbitrary, right? So you let me take first C1 equal to 1 and C2 equal to 0. In that case, yx equal to, this is one solution, one non-zero solution. Y1 equal to C1 times cos mu x. No, mu x is we already know, right? So mu x is this, so you'll put it here. So this is one solution. For example, if you take C1 equal to 0 and C2 equal to 1, then you will get another, your y solution is this one, sine. Sine is also another non-zero solution. Basically, what you are seeing is your eigenvalues are 1, 2, 3, and so on, but they are repeated eigenvalues. Okay, so you'll have two eigenfunctions. corresponding to each eigenvalue, okay, you have two linearly independent solutions. Okay, so that means basically what happens, your eigenvalues are repeated. Okay, so eigenvalues are these things. These are your eigenvalues. And then any questions up to here? Fine, right? Hello?
Yes, sir.
Okay. So these are your eigenvalues. Corresponding to each eigenvalue, you have two eigenfunctions here, as you see here, and here. Okay. I don't know why it's moving. Let me. Okay, so these are your eigenfunctions. So these are your eigenfunctions. So you can see these eigenfunctions are actually orthogonal as such, because they are different, right? They are already orthogonal. That's what this calculation tells you. Okay. There it is telling that this calculation, sine and cosine, these two functions are already they are orthogonal. The way it is done. Okay. If they are not orthogonal, you will have to do by Gram-Schmidt process. But they are already orthogonal. As you can see, this one, cos b minus cos a equal to cos b plus 4n pi. So minus cos and cos b. Okay, because a minus b is 4n pi here. Okay, so cos a cos b, if you take it, this difference is basically you're getting 4n pi a minus b, isn't it? Cos a minus cos b equal to cos b plus 4n pi, you can rewrite, and you say that this is actually cos b minus cos b. That is actually because a minus b, if a minus b equal to 4n pi. So if you easily see this one here, 4n pi, the difference will be 4n pi. If you actually see b minus a, this is your 4n pi into b by b minus a. Another one is 4n pi into a divided by b minus a. Then when you take the difference, it is 4n pi. So because of this, it is actually, they are already orthogonal. You don't have to do anything. So you have eigenfunctions corresponding to n equal to 1, 2, 3, and so on. Corresponding eigenfunctions are orthogonal, already orthogonal. Okay. So you'll have sine 2n pi by b minus ax, cos 2n pi by b minus ax as your eigenfunctions associated for every n, for every natural number n. Now look at lambda equal to 0. Equal to 0 case also, you see that your solution, your equation is y double dash equal to 0. Y dash of y, this is a general solution, C1x plus C2. Apply the boundary conditions, periodic boundary condition. If you apply, C1 will be 0. And you will see that other condition is, now the solution becomes C2. This will satisfy the other boundary condition, derivatives. So C2, that means C2 is not fixed now. That means C2 can be arbitrary. I take it as 1. So if you do that, that is your eigenfunction corresponding to lambda equal to 0. Okay. So lambda equal to 0 is also an eigenvalue, and your solution is actually constant here. Okay. Now you look at lambda equal to mu square. You bring it this side, this minus mu square. Okay. So in this case, functions are solutions are e power mu x, e power minus mu x. You apply those boundary conditions when you apply. This is how you put those two equations. You write it as ax equal to 0, and you want non-zero. This determinant has to be 0. But this determinant is like exponential function, no? Is always non-zero. So that means you can actually see that this since the determinant of the matrix is non-zero, then C1, C2 has to be 0. So that means it is not an eigenvalue. Okay, those corresponding in this case not eigen. So finally, what you got is eigenvalues are like this: n equal to 0, lambda equal to 4n square pi square by b minus a whole square. You include 0 also here by putting simply n equal to 0. You will see that n lambda is 0. So you're putting them together. Okay, eigenfunctions are cos and sine. N equal to 1, 2, 3 onwards. N equal to 0, what happens? Only 1, no? This sine function, anyway, n equal to 0, if you put it, it is 0. Doesn't matter. So, but your cos function will be 1, n equal to 0. So that is how we included here also. N is from 1, 0, 1 to 3 onwards. These are all your eigenfunctions. Now, what it says, your theorem without proof that says any self-adjoint linear operator, Sturm Liouville system, will have eigenvalues and eigenfunctions, discrete eigenvalues. And in fact, eigenfunctions are also discrete, and they form complete orthogonal set. So that means any function I can write in terms of them. This is exactly your regular Fourier series. So where ANs are this, BNs are this. Okay. This is your Fourier transform. That is your regular Fourier transform. Now take B equal to 2 pi and A equal to 0. So you see that cos nx, sin nx will come naturally. Your regular Fourier series. With the A equal to minus pi 2 pi or 0 to 2 pi, whatever you do, that's how you get your regular Fourier series. And if you are doing the working with the singular sturm Liouville system, for example, Legendre equation, you just look for all the boundary conditions are these finite, no? What are the finite solutions of Legendre equation? Only those polynomials, Legendre polynomials. Those Legendre polynomials associated with n is from 0, 1 to. Those are your eigenfunctions. Already we know. So if you know this one, you can write directly any function in terms of them. That is what exactly you get Legendre Fourier series. We call it generalized Fourier series in general. Because we are dealing with Legendre equation, we say Legendre Fourier transform. Similarly, you can also work with, if you want one other example, is a Bessel series you can find. This is a Bessel equation, you look for it. But the thing is, Bessel equation is like equation domain is 0 to infinity. So you can't work with that. So make it 0 to L. Okay, so that I think it's a special case, you need not worry. Okay, if you are interested, just go through. 0 to L, we are trying to look for only one. I am fixing my lambda actually here. Okay, for each lambda, is it a lambda? Alpha. Alpha is what? Alpha is what? I think alpha is something, right? What are the solutions that you are getting here finally? Bessel, J alpha. Alpha you are fixing. Alpha is basically n square minus alpha square, no? So that's what you, this is your x square minus alpha square, usually Bessel series. Now in trying to put x by lambda x. So this is how the equation becomes in that case. Okay, so equation becomes this, and fix your alpha in your Bessel equation. The parameter is alpha, that you fix it. Now if you fix your domain to 0 to infinity, instead of 0 to infinity, you fix 0 to some L. L is finite. Okay, then you can easily see that this equation is a self-adjoint. You can easily see the eigenvalues and eigenfunctions you can calculate in a similar way, and you actually see that they are actually, because of the bound J alpha is you know, the J alpha are the solutions, Bessel function of first kind. It looks like this. It's oscillatory functions. Those roots will give me exactly what is my lambda 1, lambda 2, lambda n's. Okay, so those are your eigenvalues here. So it's in an indirect way you get your eigenvalues, and your eigenfunctions are simply J alpha of lambda ix. So in terms of them, you write your Fourier series, fx equal to sigma ci J alpha of lambda ix, where lambda i's are basically satisfying your J alpha of lambda el boundary condition. Okay, J alpha of lambda el x. Alpha is fixed, L is fixed, and because J alpha of x equal to 0 is oscillatory, those lambda i's corresponding to those roots of the zeros of that J alpha. That's how you get lambda 1, lambda 2. They are infinite, so that's how you get your infinite eigenvalues corresponding infinite number of eigenfunctions J alpha of lambda I into x. Okay, so with them, if you write, that is your Bessel Fourier series. Corresponding CIs, of course, you do using the dot product, you get those CIs. Those are your Bessel Fourier coefficients or Bessel Fourier transform. This is your Bessel series is actually Bessel Fourier series actually or Fourier inversion inverse. Okay, inverse Fourier transform if you want to call it. In general, you can start with any equation like this, second order equation with boundary condition, regular case. It will give you, again, this is another example you can just look for, but it's difficult to find the eigenvalues and eigenfunctions. Just go through it, you will understand. Here also you will get generalized Fourier. You call it, because you don't have a name for it, so we are calling generalized Fourier series. Like that, Fourier series, you can always get it as a coming out of a sturm Liouville system. That's what I want to convey from this presentation. Okay. Any questions here? Hello.
No, sir.
You followed, right? Just go
Yes,
through
sir.
this.
Yes, sir.
Now we can get back to our problems. Okay, so what are the problems that we are dealing? For example, earlier you have seen, no? So if you actually see, did we look at the earlier? Did I send you what did we do in lecture 21? Lecture 21, and we are dealing with. You just open that lecture 21 from your WhatsApp. So we see that those you have a solutions, right? You have a solutions that we wrote. isn't it? So let me open that and show you for you. So what is that you have from your 21? Can you see now your 21? Lecture 21, can you see now?
Yes, sir.
It is there, right?
Yes, sir.
Yeah, okay. See, I'm from my slides, you can see, right?
Yes,
Yeah,
sir.
you can see. You can see. See, this is what finally what we did. We're getting back to this, and we have some flows, and then finally we're looking at the solutions of the Laplace equation. See, these solutions of the Laplace equation, what you are seeing is I'm looking for solutions in the form of separation of variables. This separation of variables, when you are doing r of r, theta of theta, so you see this one is one equation is you put it in this equation, cylindrical coordinate system. Actually, we are in only in 2 dimensions, so cylindrical need not worry. We simply write only this one, right? So you're only asking for polar coordinates. So d square phi by d dou z square, anyway take it as 0. In polar coordinates, if you take it, and you see now substitute, and you are seeing that variables are separated, like in your separation of variables, and this will be real constant. This real lambda, this is a real or not, we don't know. So you make it like you have 2 ODEs you got. Now look at this theta double dash plus lambda into theta. This is like your sturm Liouville system, right? If you take theta being your periodicity, theta is polar coordinates, no? Theta at 0 and theta at 2 pi, capital theta of theta, small theta at 0 or 2 pi should be same. Similarly, first derivative also same. So if you apply your periodic boundary conditions to this second ODE, then you will have a sturm Liouville system. All your Fourier your eigenfunctions are all, what are your eigenfunctions? Sin n theta, cos n theta, right? So what are the eigenvalues? N is from 1 to 0, 1, 2, 3 onwards. So if you put here, what is this equation? First equation. Now I'll open that actual file from then we'll write it. Okay. So let me open that and we'll see. Okay. So where is that one? Yeah, you can see that now in this. Now I can. Okay, these are the 2 equations that you got. Okay, so with the presentation that I have done just now on regular sturm Liouville system, so this equation with theta, let me. Okay, so now if I do it, yeah, this theta double dash of theta plus lambda theta of theta. Take it this the right hand side. Okay, where theta is between 0 to 2 pi. Okay. Remove it, so it's both are same. Okay, and then you have theta of 0 equal to theta of 2 pi, theta at dash of 0 equal to theta dash at 2 pi. These are your boundary conditions, isn't it? Periodic boundary conditions. So this will give me eigenvalues. What are the eigenvalues? Eigenvalues are n. N is from 0, 1, 2, 3 onwards, isn't it? Eigenfunctions, cos nx, sin nx.
Yes, sir.
N is from 0, 1, 2, 3 onwards. Because we are considering b equal to 2 pi and a equal to 0, so b by a into that that will go. Okay, so once you substitute, this becomes only cos nx sin nx, the usual Fourier series that you are getting. So you put these eigenvalues into your first equation and then make a product. Okay, so let me go to the second page and then we'll work out. So what is that equation that you are getting? R square. You have class now?
Yes, sir. We have class from 12.
r minus lambda. I'm leaving you soon. Okay, so r of r. This is actually your Bessel Euler-Cauchy equation. So what are the solutions here? You already have cos. What are the solutions here? What are the solutions here? Linearly independent solution. What is your r of r? I'm not going to do just to calculate. Okay, so I'm going to get it here as this is the second order equation. Cauchy, go and work out. Okay, so this you will get it as some C1. Yeah, what do you get? R power m, isn't it? R power n plus C2 r power minus n. Corresponding to the case n is from 1 to 3 onwards. Okay. And what happens when you put n equal to 0? If n equal to 0, then this becomes simply equation this one. Okay. You don't work with 1 by 1 r will go. So if you actually solve this one, what you are getting? So simply log r, right? Yes.
Yes, sir.
Log r only, right?
Yes, sir.
You will get log r as your solution. Okay, natural base. Of course, so constant is also there, right? C1 plus C2 times log r. You verify, okay? So you verify, go and verify and let me know. So now what you do, correspond to the case cos nx here, sin nx, this one. That's what you need to put, no? So those are the solutions. Now we can write the solutions now. So this implies, what are your solutions? Let me write it now. Phi of r theta, your solutions finally become, what will become? Your final solutions? Can you give me those solutions? Those solutions are constant. Constants we are not interested, no? So finally you take C1 here, n equal to 0. This C1 and finally cos nx, sin nx. 1 into cos nx, 1 into sin nx, put n equal to 0. That becomes simply constant, no? So I'm not interested because constant, if you differentiate, that will be 0 in your flow velocity. So for constants, you are not interested, but still if you want, you can write it. So C1 cos 0, that is 1. Okay, some constant plus another constant. So, okay, I'm going to, these are the constants already we wrote. So we'll write it here as A0, for example, some A0 constant times, that is one solution. Other one, what else? Other one, A1 times log r. Log r corresponds to n equal to 0. And cos nx only will contribute, that is 1. Product is 1. So the log r plus, what else you have? Now we are writing, corresponds to n is from 1 to infinity. I'm going to put it like an. N is from a we already wrote, no? So you put it as a minus 1 and a0. Okay, so like that. So that n is from 1 to infinity. An, and now I can take r power n. Okay, so just put it a power r power n plus C2, I'm calling it as bn, r power minus n. Okay, this you multiply with cos nx sin nx, right? So cos n theta plus, again you repeat, so an or you call this, those numbers, those constants need not be same, no? So let's call this some c and dn. So cn r power n plus dn r power minus n. This multiplication is sin n theta. So these are all your solutions. Okay, this is with your sum. So these are all possible solutions if theta is periodic variable, isn't it? If you don't, and what are the other solutions that you can find for the Laplace equation? And P of r theta is simply C1 r plus theta also, no? Isn't it? Hello?
Yes, sir.
N equal to 1. C1 r. These like this also you can do, no? So the theta and C1, C2. These are also possible. Linear functions, right? Linear functions are always solutions of Laplace equation. That is what we have already seen earlier as your one of the flow where we used theta equal to simply you take what did you use? Yeah, k theta. Simply theta as your phi theta. Okay. So this is one we have seen. Okay, so we will look into what we do now is instead of taking some function and then look at the flow, now we are considering all the solutions of Laplace equation and we will see what are those flows. Some you might have already seen, some new flows will come out of all these functions. Okay, so that's what we will see in the next class. Tomorrow and day after tomorrow, I'll try to finish. Okay, so this with these flows, we'll look into these flows, natural flows. That is the only aim is to look at flow past cylinder. Okay, keeping that's what we are finally interested. The motivation coming from flow past cylinder you are interested to study. Okay, so we'll see that one in the next class. Okay, so
Okay, sir.
you have another class now. So
Yes.
please inform everybody that I want to take tomorrow day after Friday and Saturday also. Before I come there, I'll try to take and try to cover some this simple mathematics only. If you have doubts, please ask me immediately. I'll clear. Okay, don't keep as incomplete so that you'll understand everything. Okay, there won't be any doubts. Okay, so I'll see you tomorrow again at
Okay.
10. Okay, yeah.
Thank
Bye.
you, sir.
Thank you, sir.
Thank you. Thank you. Bye.